Good afternoon, class. Today we're going to be looking at, this assignment has several distinct topics. Systems of equations. We'll look at matrices and augmented matrices, and as well as Cramer's rule. I think I'll stick on a and Cramer's rule here. That little symbol there is an and. And we're going to split this assignment up into two lectures because there's so much stuff in it. We're going to start off looking at a system of equations.
What is a system of equations? You keep saying that.
A system of equations is just two or more equations written together. Two or more equations written together. Or grouped together, however you want to think of it. And we're going to be solving a system of equations. To solve a system of equation means to find the point or points of intersection of their graphs. I'll say to solve a system means to find the point or points of intersection of the graphs. And let's think about lines.
Let me show you. Look at this first problem, and it says, solve the following system of equations. Notice there's no exponents. So what sort of graphs are these? Starts with an L.
A line, okay.
Yeah,
so let's look at the possibility. When you're looking at the two lines intersecting, the most common situation, you have two distinct lines intersecting in one specific point, one unique point. That's the most common situation. There's one unique solution, okay?
Is it possible to have two lines intersect at exactly 2 points?
Say no.
No, you can't have two lines intersecting 2 different points.
Okay. The second possibility, let's see, how about parallel lines? How many points do they have in common? Parallel lines, we know they never intersect. So how many points of intersection would there be?
0. I heard it right.
So there are no points of intersection. No points of intersection. And the third situation, one that most people don't think of, they're called coincidental lines. Let me write that out. C-O-I-N-C-I-T. Coincidental lines. For our purposes, coincidental lines are lines that are just one on top of the other. I'll say one line on top of the other.
Sticking with the red and green, if you had the red line right on top of the green line.
Okay, so you have a red line and you have the green line right on top of it. How many points of intersection are there? How many lines do they have how many points do they have in common? Every one of them, right? So there are infinitely many points of intersection.
The interesting cases And we'll see this with the word problems, of course, where there's just one solution.
We're going to look at two methods of solving a system of equations, and there's, we're going to see a third method on Monday, but now we're looking at two. There are two generally accepted algebraic methods of solving the system. So, okay, I'll say two methods of solving that we're seeing today. The first method, I think I'll Roman numeral them. The first method, substitution. With substitution, you need one of the equations solved for one of the variables. And then whatever that expression is, you substitute it into the other equation. To illustrate, let's look at number 1. Here they're telling us to solve by substitution. Even if they didn't tell us to solve by substitution, this problem is tailor-made for the substitution method, because you'll notice one of the equations is already solved for one of the variables. The second equation is solved for x. So let me write these problems down. We want to know, where do these two lines intersect? 5x plus 6y equals 3. And the other equation is x equals 18 minus 7y.
You'll notice there's these options here, infinitely many solutions and no solution. We'll discuss how you can tell if it's that in a moment, after we do problems 1 and 2.
Right. Mm-hmm. There's an easy way of spotting the infinitely many or no solution situation. So, but notice, this system is tailor-made for substitution because one of the equations is already solved for one of the variables. So what you have to do, just like the name substitution implies, you're going to take that other stuff, the stuff that that second equation solved for, and you're going to substitute it for x in the first equation. So we're going to have a 5. But in place of the x, we have that 18 minus 7y.
So you're going from two equations with two variables. You're about to write one equation with just one variable, correct?
That's correct. Notice there's no x's appearing here. This equation only has one variable, y. Well, we know how to solve this equation. We got to get rid of the parentheses, combine like terms, and then get y by itself. So the first thing I do, I distribute the 5 over the 18 minus 7y. 5 times 18 is that 90 minus 5 times 7y is 35y. And we still have a plus 6y is equal to 3. We need to get the y terms by themselves on one side. Let's combine the negative 35y plus 6y. Negative 35 plus 6, is that a negative 29y? I guess I'll go 90 minus 29y is equal to 3. I'm trying to get the y term by itself. You know something? Let's do this in a way so that we minimize negatives. Let's take that negative 29y and move it over. Then we'll take the positive 3, move it over to combine with that 90. So on the right-hand side, we're going to have a positive 29y. What are we going to have on the left side? What are we going to have to do with the 90 and the 3? When that 3 comes over, it's no longer a plus 3. It is a minus 3. 90 minus 3 gives me an 87. And now we need to solve for y. We can divide both sides by 29. Give us y equals, let's see, 87 divided by 29, is that 3? We've just now found, we're trying to figure out where do these lines intersect.
Notice it says type an ordered pair.
We're looking for an ordered pair, and we know the y value. The y value is 3. We already know that y value. What will we do to find the corresponding x value? We were able to algebraically find the y value to be 3, but how will we find the x value? What's the name of this method? Substitution. We're going to substitute. Substitute the 3 for y into one of the two original equations. My advice to you, substitute the what you're trying to find x. Use the equation that's already solved for x. Use that, what was it, x equals 18 minus 7y. Plug in a y value of 3. So you're going to have x equals 18 minus 7 times 3. I'm replacing the y with 3. 7 times 3 gives me 21. So what's the x value of this ordered pair going to be? 18 minus 21, I agree with negative 3. That means that these lines intersect, these two lines intersect at the unique point of negative 3, 3. Solving a system of equations means you're trying to find the point or points where the graphs intersect.
And you can check your answer by plugging it into both equations.
3 times, plug in the x value, that's a negative 15 plus 6 times 3 is 18. Negative 15 plus 18, sure enough, it gives us a positive 3. Any questions there? When using substitution, you have to have one equation solved for one of the variables. And if you're going to use substitution and you don't have one of the equations solved for one of the variables, you're going to have to rewrite one of the equations so it is in the form either x equals or y equals. Let's look at number 2.
Well, wait, I thought I typed in the answer.
Oh.
Notice you've got to put the parentheses. If you don't, it's going to count it wrong. You've got to type it as an ordered pair. So problem 2 is another substitution. I like this one.
We want to know, where does the line 5x plus y equals 23 intersect the line 8x minus 2y is equal to 26?
Wait, you said 26, but it's 23. Yeah. Oh,
5x plus y equals 23. 8x minus 2y equals 26.
You got it right. I misheard it.
Instructions say to use substitution once again, but unlike the previous problem, we don't have one of the equations solved for one of the variables. Well, there's one equation here that would be real easy to solve for one of the variables. You wouldn't pick up any fractions. Now, if I have to solve a system of equations and in order to use substitution, I have to pick up a fraction within the equation, I don't use substitution. That other method, elimination, would be better, and we'll see that in a moment. But here, look at that first equation. Wouldn't it be easy to solve for y? You wouldn't want to solve down here for x or y because you'd have to divide by 8 or divide by 2. You'd be picking up fractions along the way. The easy one to solve for is the first equation, get y by itself. So you're going to have a 23 minus Move that 5x over. So there's the revised first equation. Then I will take 23 minus 5x. That goes into the other equation in place of y.
So what you've done, you isolated one of the variables and then plugged that into the other equation.
If you're doing this correctly, you shouldn't have x's and y's in the new equation. We have an 8x minus 2 times 23 minus 5x.
Linear equation.
Get rid of the parentheses, combine like terms, get the x on one side, get it isolated on one side, and
number on the other.
I think we need to distribute that -2, so we have 8x. -2 times 23 is a minus 46. -2 times a -5x gives me a plus 10x equals 26. We can combine the x terms. 8x plus 10x gives me an 18x.
Y'all caught up? Isolating the variable, solving.
Okay, what do you think I'm going to do next? Add the 46. Yeah, that's what I'm going to do. So I'll have an 18x equals, I'm adding 46 to both sides. 26 plus 46 gives me, is that a 72? Divide by 18 to give me x equals 4. That says that the lines, these two lines intersect at an ordered pair where the x value is 4. Here we have x first. A moment ago, we got the y value first. It just depends on which variable you're solving for, which one was isolated. In the first one, we solved for y and then substituted to get x. Here, we got the x value first. These things are going to intersect at an ordered pair where the x is 4. Well, how will we find the y value? Well, just like the name implies, we're going to have to substitute. Go to the form where the y variable is already solved. That's the easy one to plug into.
So there's nothing wrong with doing it in the other two. It's just going to be more work.
So we have y equals 23 minus 5 times x. X is 4. 5 times 4 is 20. To give us y equals 23 minus 20 gives me a y value of 3. For my ordered pair, my point of intersection is the unique ordered pair 4, 3.
If I can interrupt, now we can check it. Plug a 4 in for x, a 3 for y. 5 times 4, 20, plus 3. Does that give 23? Yes. 8 times 4, plugging into the second equation, 32 minus 2 times 3 is 6. So 32 minus 6, 26. So let me type that in. You know it's right. Of course, I'm going to get this counted wrong because, and they don't even know what's wrong. They just talk you through. Solve for one of the equations, plug it in. Okay, what did I do wrong here? No parentheses. Click there. Put the parentheses around it.
Come the final exam. If you do that, even if you have the x and y correct, then Without the parentheses, MyLab's going to mark it wrong. If I notice it when I'm
that's
reviewing.
part of the thing, trying to look through every test for that.
But
since every prop test is in a different order. It's not like, well, I got to just look at everyone's 13 and 14. No, I've got to find it on your test. So,
type an ordered pair means enclose it in parentheses. Now let's go back to those special cases a moment ago. Let's see. Where is it? Right here. One unique solution. We've just seen that in problems 1 and 2. Suppose we were going through all of this and everything subtracted out. The y term subtracted out and the constant term subtracted out. You're at this point here where you're trying to get the y by itself, and if we had a, let's see, a negative 35y, suppose that had been a plus 35y, the y terms would have gone to 0. Suppose the other terms go to 0 as well. Suppose you'd had a 3 and a minus 3, so you wound up with 0 equals 0.
A 3 and a 3.
Yes, a 3 and a 3, so 0 equals 0. If you're going through using substitution, it's also true for elimination, which we'll be seeing in a moment. If you're going through using substitution or elimination, and you wind up, your variables cancels out, and your constant terms subtract out, then you're looking at a situation where there are parallel lines. There's no point of intersection, so you would have selected option C. No, I said it wrong again, didn't I? Coincidental lines are 0 equals 0. Forget what I just now said. And you just let me go along, okay? 0 equals 0. When does 0 equal 0? Always. So when do the lines intersect? Always. For parallel lines, it's 0 not equaling 0.
You get some number.
Suppose the y or x terms all subtract out, and you get 0 on one side, but a non-zero on the other side. Those are parallel lines. When does 0 equal a number other than 0? Never. When do the lines intersect? Never. So the funny thing, I did this last year too. It's one of those things that my brain is beginning to flip around, which is sort of bad. I know. And so let's make a note. One unique solution, the most common situation. Parallel lines.
Maybe like 0 equals non-zero or something.
You wind up with 0 equals a non-zero.
It's not equal, like 0 equals 0.
But for coincidental lines, when do they, and it's easy to remember this because of the way I say it. Coincidental lines, one on top of another, they always intersect. Well, 0 always equals 0.
Parallel lines, 0 never equals a non-zero number. 0 equals 3 or something. I don't think there's any that show up like that in the assignment.
But if it does, if you regenerate and it gives something like that, you're going along where the variable cancels out. If the variable is subtracted out and you don't have an x or y, it's one of the two special cases. And number 3.
The natural question is, well, what would we do if you couldn't easily get one of the well, heck, this one, we could do this with elimination.
Yeah, we could.
With substitution.
But the instructions say to use elimination, and so
elimination is the preferred method.
I prefer elimination. If I have to choose, I never use substitution. If it's up to me, I'm going to use elimination. I guess at problem 1 Problem 1 was just really tailor-made for elimination, the way they had one of the variables solved for the other one.
How often do you get that?
That's right. How often do you get that? This is number 3.
And you'll be able to say how often you get that when you're doing the word problem.
Equals 72. And the other one is a negative x plus 8y equals, is that 56?
Mm-hmm.
We want to know, where do these lines intersect? If we were to draw the graphs, where would they intersect? With elimination, you have to make sure that your like variable terms are aligned and you have the constant terms by themselves on the right hand side. You have to have the x's lined up, the y's lined up, and then on the other side the constant terms. What you need for elimination, you need the same coefficient on one pair of variables but with opposite signs. Here we have an 8 and an 8. Note they don't have opposite signs on the y, but look at the x's. I think this one is tailor-made for elimination. The coefficient for this x on top is a positive 1. The coefficient for this x here on the bottom is a negative 1. That's right. So once you have the like variables aligned and they have opposite coefficients, then add the two together. 1x plus a negative 1x, what's about to happen there? X minus x. We've eliminated the x's. The x's are gone, hence the name elimination. Now, continue adding though. 8y plus 8y, that gives me a 16y. 72 plus 56 gives me a 128.
Notice how fast you got to that step. If you were doing substitution,
you'd have to go through and distribute and combine like terms.
Mm-hmm.
And now it's a simple matter to solve for y. Just divide both sides by 16 to give us y equals, is it 8? What's 128 divided by 16?
80 and 48, yes, 8.
So keep in mind what we found. We found that these lines are going to intersect where the y coordinate is 8. The y coordinate is 8. In some older books, when using elimination, they use strict elimination, okay? Now, they're going to go back through, they're going to have to change one of those 8's to a negative 8 and eliminate the y's to solve for x. But that's pretty much archaic. No one does that anymore. What people do with elimination, they use a combination of elimination and substitution. Once you use elimination to solve for one of the variables, you can substitute that value in to get the other variable. You have to go back to one of these original equations. I think, which one looks less painful? I think the first one, there's no minuses appearing or anything. I'm going to substitute into that first equation. X plus 8y equals 72. So substituting in 8 for y, we have x plus 8 times 8 is 64. And subtract 64, what's that going to give us for x? I guess that's not a very interesting.
Yeah, this isn't a good example.
It looks like we're getting an x value of 8 as well.
By no means are we saying it's always going to work out like that. That's just a
coincidence.
The numbers, the 8, 8.
Mm-hmm. But you'll use elimination to solve for one of the variables, and then you'll substitute to find the other variable. And that's the standard method of elimination. No one uses strict elimination anymore. It has been years since I saw a book where they eliminate to find one, then they eliminate to find the other.
That only would work for linear.
Mm-hmm.
Let's see if the next one is oh, I like this one.
Really? Okay, this is number 4. I'm going to write small so it fits on here. Oh, goodness. 9x plus 4y equals a negative 36. And 9x minus 4y equals a negative 108. Glancing at this for a moment, I thought it was going to be a special case, but let's say minus.
That's just pretty negative here.
Okay, looking at this equation, notice we already have the like variables aligned. We have the constant terms by themselves on the other side, and I claim that it's already in the form that's set up for elimination because look at the coefficients of y. We have a positive 4 as one coefficient. We have a negative 4 as the other. So we have what we need. We need we need the same coefficient but opposite signs. And I think we have that. So we can start adding them together. 9x, I don't see a sign there, so that's assumed to be plus. 9x plus 9x is 18x. What's about to happen when we try to add the y's together? Positive 4y plus a negative 4y. Sure enough, we've eliminated the y terms. They've gone to 0. Negative 36 minus 108, is that a negative 144? So to solve for x, we'll have to do what? Divide by 18. So that's going to give us x equals 144 divided by 18. Is that
8.
8?
80
8.
And
It's another 8?
64. Negative.
Negative, thank you.
So if in doubt, just guess 8 is the answer. I'm joking completely. You just have a run of a lot of 8s. It's just a coincidence.
So the x value is negative 8. We're going to have to plug in to find the y value. I'm going to use the one that has the smaller number, the negative 36. Oh, technically, I guess it's bigger, okay? But the smaller magnitude, I'll say. I'm going to use that 9x plus 4y equals a negative 36. You plug in 8. Plug in negative 8 for x. 9 times negative 8 is a negative 72 plus 4y equals a negative 36. I'd add 72 to both sides. It'll work it out pretty nicely. 4y equals negative 36 plus 72. Is that going to give us a positive 36? I went plus 72 plus 72. I added the 72 to both sides, and that's how I got 4y equals a positive 36. And then all that's left to do is divide by 4 to give us the y value of 9. So those two lines, 9x plus 4y equals a negative 36, and 9x minus 4y equals a negative 108, intersect at the one ordered pair, negative 8, comma 9. Any questions there? Oh, let me box in my answer.
Let's put in negative 8, comma 9. Negative 8, comma 9.
Any questions there? Now I want to do one. I want to do that one and then do 5.
Yes.
Let's do ours. Okay. Give me a moment.
Here's an example.
This is an example. 9x plus 4y equals negative 36. And this is similar to the one we just did, okay? And then negative 9x minus 4y equals a negative 108.
All you did was put a negative in front of that second 9.
Okay, in front of that second 9, I stuck a negative sign.
And you'll see, hopefully you'll see what we mean by...
Look at that. The x's have the same coefficient but opposite sign, and the y's have the same coefficient but opposite signs. One positive, one negative. Let's try to add these two together. We're going to eliminate the x's. 9x minus 9x is 0. What's about to happen to the y's? We've eliminated them as well. 4y minus 4y equals 0. So all the y's, the x's and y's eliminated. We just have a 0 on the left side. Now if we have a 0 over here, that means they're coincidental lines, infinitely many solutions. If we have anything other than a 0, then you're looking at parallel lines. Negative 36 minus 108 gives me a negative 144. 0 never equals negative 144, so these lines never intersect. They're parallel lines, which means there is no solution.
Yeah, I think that's how they say it on there.
What are they? I'm writing it out. I bet they use the little no solution symbol, the empty set, do they?
No, they just say there's no solution.
Oh, well, good for them. Okay. That's what I mean when I said that you can spot those special cases. The variables have to subtract out. If you'd wound up with a 0 equals 0, coincidental lines, that would have been response B. Let's see.
Infinitely many solutions.
Infinitely many solutions, that's right.
Now, going back to what you wrote right. Oh.
Where is it?
Oh, wow. This statement right here. Does that make more sense? 0 equals non-zero.
That means there's no solution.
If you'd wind up with a 0 equals 0.
For coincidental lines, you would have had 0 equals 0. There are infinitely many solutions. Every point on both lines is common to one another. Infinitely many solutions.
I don't recall ever getting those answers.
Mm-hmm.
But if they do, if that happens, it's easier.
Yeah, it is. Because as soon as those variables subtract out, it's one or the other, either infinitely many or no solution. What's number 5?
Number 5?
Solve using elimination. Well, I see a problem here. I see something here that I don't hear.
X and Y's are lined up, but if we just add them vertically, I think we'll get an 11x and a 2y. We're not eliminating one of the variables. With elimination, you're adding vertically.
Okay, so make sure that miscopy.
Negative 11, 3x minus y was negative.
Okay. Once again, they want us to use elimination. And I see a big problem. The variables are aligned, but we don't have the same coefficient on a pair of variables. We don't have, there's an 8 and a 3. Hey, well, look at this y. At least we have the opposite signs. I have a positive 3y there. I can change this to minus 3y, the second equation, by multiplying 3 by 3. That's like a 1 right there. That's a minus 1y. We know whatever we do to one side of the equation, we have to do to the other. You can multiply both sides by any non-zero quantity you want. I'm going to multiply the second equation by 3. I'm multiplying 3 by 3. The first equation is going to stay 8x plus 3y equals a negative 11. But that second equation, it's going to become a new equation. 3 times 3, that's a 9x. Distributing that 3 times a negative 1y, that gives me a minus 3y equals 3 times a negative 2 gives me a negative 6. You see why I multiplied by 3 on that second equation. Try adding these two equations together. That's a positive 9x. 8x plus 9x, that's a 17x. What's about to happen to the y's? Positive 3y minus 3y, we have just eliminated the y's. The y's are gone. Negative 11 plus negative 6 gives me a negative 17. Oh, this works out very nicely. Divide both sides by 17 to give me x equals negative 17 divided by 17 gives me a negative 1. That means that these lines, these two lines, are going to intersect at an ordered pair where the y value, not the y value, the x value is negative 1. So we need to substitute to find the value of y. We know x is negative 1. It doesn't matter which equation we use of the original equations. You could use 8x plus 3y equals a negative 11, or you can use 3x minus y equals a negative 2. Which one do y'all want to use? This one has more minuses, but the numbers are smaller. I think I'll use the first one.
I was going to say I'd use the first.
8x plus 3y equals negative 11. Let's plug in that negative 1 for x. Here we go. 8 times negative 1 gives me a 8 times negative 1 gives me a negative 8 plus 3y equals negative 11. Add 8 to both sides to give me 3y equals negative 11 plus 8 gives me a negative 3. And divide by 3. It's just a coincidence. They're the same number. The x value was negative 1 and the y value was negative 1. I don't know if we're getting
lucky or unlucky with these numbers. Not sure.
Any questions there? Substitution and elimination. My preferred method is elimination, because you don't have to have one of the variables solved for one of the one of the equations solved for one of the variables. Like on number what is it? This number 4, I certainly wouldn't want to use substitution, because regardless of which variable you're going to solve for, you'd have to go through and you'll wind up either with, if you solve for x, you'd wind up with a denominator of 9. If you solve for y, you'd wind up with a fraction and a denominator of 4. So if you're trying to avoid fractions as much as possible, elimination is better than substitution.
In fact, all you got to do to convince yourself is do number 4 or 5 by substitution. Start it off and you'll see, oh, that's why he prefers elimination.
Well, this one wouldn't be bad, number 5.
You still got to move that, move this, and you got to distribute. It's going to be a much messier equation. And 17x equals negative 17.
Any questions there? Okay.
Leaving that behind us. Oops, what am I doing now?
Oh, I got to write some. A matrix, M-A-T-R-I-X, is a rectangular arrangement of numbers. A rectangular arrangement of numbers. The plural of matrix is matrices. The plural is matrices, M-A-T-R-I-C-E-S. And a matrix is just any rectangular arrangement of numbers. It's standard to enclose matrices in big rectangular brackets, like what you use on for interval notation. And here's an example of a matrix. I'm going to write out a matrix for us. I'm just going to make it up. Let's say 1, -3, 7 on top, and 0, 5, 1/3 on bottom. The horizontal alignments are called rows. So this is row 1, and this is row 2. The vertical alignments are called columns. So we have column 1, column 2, and column 3. When I'm looking at this matrix, we can determine the size based on the dimensions, the number of rows by the number of columns. Think of a rectangle. If I wanted to come in here and put carpet on this floor, I had to measure the dimensions of this floor. I wouldn't just come in and say, oh, the dimensions are 40. I need it in terms of the length and the width. The size of a matrix is the same thing. It's given in terms of the number of rows by the number of columns. That's how you measure or express the size of a matrix.
So X is by, not times.
Mm-hmm. Mm-hmm. So we would say this is a 2 by 3 matrix. 2 rows, 3 columns. Now if you multiply that together, 2 times 3, that says there are 6 numbers inside that matrix, but you don't have to worry about that. Here's another example of a matrix. Let's consider this matrix. Okay, that's all discussion right there. Okay. How many rows do we have here? The rows are the horizontal alignments, so we have 3 rows. How many columns do we have? The columns are the vertical alignments. So 3 rows, 3 columns, C-O-L-U, okay, there. That means that we have a 3 by 3 if the dimensions are the same, just like with a rectangle. If you have a 3 feet by 3 feet rectangle, we call that a square. If the 2 dimensions are equal on a rectangle, we call it a square. Likewise, a 3 by 3 matrix, we call that a square matrix. I want to mention that because In a little bit, we're going to be finding determinants for square matrices. I think I'll write that out. A square matrix has the number of rows equal to the number of columns. The number of rows is equal to the number of columns. And that agrees with our geometric interpretation or definition of a square. Isn't a square a rectangle whose dimensions are equal, the base times height or the length times width, whatever you want to think of? Any questions so far? There's another type of matrix, let's see, called an augmented matrix. An augmented matrix summarizes the coefficients and constant terms of a linear system of equations. It summarizes the coefficients and constant terms of a linear system.
Are we ready to do probably all this stuff?
There's also something called a coefficient matrix. A coefficient matrix just summarizes the coefficients, not the constant terms.
Wait, I never put in the answer to number 5. Oh, wow.
-1, -1.
Oh, yeah. -1.
Okay.
Now, let's look at number 6.
Write an augmented matrix for the following system of equations. Let me write this problem down. This is number 6.
Wow. Seems like we've been going for so long, and we only have a 40.91 at this point.
Negative 3x plus 4y is equal to 8, and 9x minus 2y is equal to 9.
Augmented matrix.
Okay, switch to my paper.
I wanted to mention this vertical bar. But
okay. When you're setting up an augmented matrix, each equation will be a row. We have 2 equations, so we're going to have 2 rows in our matrix. You have to make sure that the like variables are aligned on the left side of the equal sign. The constant terms have to be on the right side of the equal sign. So we're going to set up, we're going to have 2 rows because there are 2 equations. Then you summarize the x coefficient. Since that's the first variable written, you'll write that column first, -3 and +9. The second column will summarize the coefficients of y. That's a +4 and a -2. With an augmented matrix, to denote that equal sign, you draw a vertical bar. That's what Anthony was mentioning there a moment ago. And then the column of constants, which are on the right-hand side, 8 and 9.
Typing in -3, 4, 8, 9, -2, 9.
All we have to do is set up augmented matrix, set up an augmented matrix there. Now, if you take Math 1324, or if you take linear algebra, you're going to do a lot with augmented matrices, okay? But for our purposes, all we have to do is set them up. We have to be able to set them up, and we have to be able to interpret them. Let's look at the next question.
Last time you didn't write it out. This one, you just typed it in. This is one of those problems you can probably do just when you're doing your homework. Just type it in without a lot of writing.
But everyone else is writing it down, Tony, because...
I know.
So I'll write it down.
Okay. But you did it last year, is all I'm saying.
Last year we did the entire assignment all in one time, and so we were in a hurry. Here we have time to... Okay. And 2y minus 2.
Notice how.
Wait a minute. Negative 5, 3.
Are the like terms lined up?
Are the like terms lined up when you look there? Is this system written in the order in which we need it? Yes. Okay. So there are three equations. So our matrix is going to have 3 rows. The first column is going to summarize the x coefficients. We have a 5 and a 3. Uh-oh. What have we got here? I don't see an x term. So if there's a missing term, you treat that like 0 times x. So for a missing term, the coefficient is 0. For y, we have a -8, a -7, and a +2. For z, we have 3, 8, -2. We draw our vertical bar. And then the coefficients are -9. The constants, thank you, are -9, 3, -5. Just for the record, what size is this augmented matrix? How many rows do we have? 3. How many columns? 4. So this is a 3 by 4 matrix.
-8, 3, -9, okay. -7.
I guess we didn't really need to write that out, did we?
Gotta put a number, 0, 2, -2, -5.
Now, in classes like Math 1324 and linear algebra, we take augmented matrices and we do something called elementary row operations to rewrite the matrix so that we have 1s down the diagonal and 0s everywhere else. Now, why would we want that? If we could go through, and we could go through, I'm getting ahead, aren't I? Okay, well, now we're going backwards. We're going backwards. Here they're giving you the matrix, and they want you to write the system of equations. So this is number 8. Let me write the matrix. And 3, 0. Okay. A quick glance shows that they're using the answer format. They're using X, Y, and Z. So switch over to my paper. The first column will be the coefficients for X. the second one for y, the third for z. So that first row there says 1x, and that's a positive 8, so plus 8y, and a minus 6z is equal to 3. The second equation, it says 0x, so we won't even show that 0x. We'll leave that spot open. That's a positive 6, so we have a positive 6y minus 1z, so I'll just say minus z is equal to negative 8. You tell me what the third row is saying. 3x. Okay, so there's no y. That's a positive 5 there. So plus 5z is equal to 4. And my lab is so nice. All you have to do is go through and fill in some blanks. That's a plus 8. Oh, be careful this next one. I'll get students emailing me that they're getting it counted wrong because they'll type in the minus z or negative 6. But notice they've already put the minus sign there for you, so you just type in the 6. And then that's a 3. And then 6 minus z equals negative 8. And 3x plus 5z is equal to 4.
It's lined up real pretty, but
this is still science fiction 40 years ago, Tony.
Yeah.
If we were taking this class, it would be science fiction. Okay, now coming back to what I was mentioning, notice how this matrix is a special matrix. We say that it's in reduced echelon form because there's ones down the diagonal. Start in that upper left-hand corner. Do you see there's ones down the diagonal? And above and below those ones are zeros. Now, why is that form desirable? If we can take a messy matrix like the one in numbers 7 or 8 and reduce it so that we just had ones down the diagonal and zeros elsewhere, look at what we would get. This is number 9. Let's see. Let me write it down. Okay, and when you read the instructions, they say to use the letters X, Y, and Z. And they want us to go back from the matrix to write out the equations. Switch to my paper. And they've told us which variables to use. They said use X, Y, and Z. That first equation, that says 1x, and then that's a plus 0y plus 0z is equal to 9. Clean up that equation. That reduces very nicely, or cleans up very nicely. We know 1 times x is just x. What happens to the 0y and the 0z? They're gone. So that first equation is really just saying x equals 9. Go down to where the 1 is, move across. That number on the right hand on the right hand column is the solution value for x. With that in mind, what's the second row saying? We have no x and no z. That says 1y is equal to 1y is equal to 3. What's the last row saying? Okay, z is equal to 2. And for if you're interested in this matrix reduction, take Math 1324 or linear algebra. To take linear algebra, you got to get a few calculus classes under your belt also before you do that. But if you have one of the, pull up the calculator. Okay, let's see, where is
Matrix is right there.
Okay, right underneath the math key it says matrix. So go second matrix. Notice it's in yellow. So there and there you have to set up a name. And
edit.
Okay, edit. Okay, for something like, I'm not going to go through and reduce get a matrix, but we could use this. It'd be easy enough to say, okay, this is a 3x4 matrix, and then go through, putting in the numbers, 1, 8, negative 6, 3, putting them in, and then the calculator will go through and reduce it for you, giving you the ones down the diagonal, the zeros elsewhere, and then the numbers on the right hand side would be the solutions for X, Y, and Z. Of course, if you can't get ones down the diagonal and zeros elsewhere, that means there's not a unique solution. But if there's a unique solution, you can use your calculator to easily reduce it using matrix reduction. Any questions
and
there?
I have
Once
videos
again,
of it on YouTube right there.
if you're
when I'm doing
curious.
it,
But for our purposes, I don't think we need to.
We need to move on.
We need to move on. Any questions?
Oh wait, did I write up the answer?
X, Y, Z.
Yeah, I think that's what everyone does.
Everyone's answer to number 9 is X, Y, Z. And y'all say that I'm too mean and stuff. I'm telling you the answer for your number 9 on this homework. So that's the Christmas present I'm giving you, okay? Oh, let's see. Did you see what I did, Tony?
I just saw.
You didn't seem to be
it.
impressed with it, okay?
I don't know how to get it there. That's what I'm trying to figure out.
It's the wallpaper.
Oh, okay.
Okay. And now determinants. How we doing? Okay. Okay, switch to my paper. I gotta write out something. Determinants
Of square matrices. We're now going to look only at square matrices. We'll eventually connect these determinants and elimination, substitution, all of that
on
Monday.
Monday. There's a connection. We're going somewhere with all of this, okay? It may seem like just random topics that we're stuck into this assignment, but no, it's all connected. Okay. A determinant is a unique number assigned only to square matrices. A determinant, each square matrix has a unique number called a determinant. I'll say a determinant is a unique number that is applied. Assigned, why does it say applied? Assigned to a square matrix. Remember, a square matrix has to have the same number of rows as columns. So number 9, that augmented matrix on number 9, that's not a square matrix. There are 3 rows and 4 columns.
So you can't find a determinant there.
Now, if we only looked at the coefficient, if we only looked at the coefficients, say a coefficient matrix, where we're only looking at the coefficients of X, Y, and Z, 3 by 3, that is a square matrix. You could find the determinant. We need to know how to find the determinant of a 2 by 2 matrix and the determinant of a 3 by 3 matrix. We'll start off with a 2 by 2 determinant. Now, to denote a determinant, if you took a linear algebra course, you'd see that determinants have many of the same properties as absolute values. So instead of enclosing a matrix in these bracket bars that we use, if you're looking for a determinant, it's standard to enclose them in big absolute value bars. A 2 by 2 determinant, that means there are 2 rows and 2 columns, A, B, C, D. This is one of the easiest things we've done this semester, finding a 2 by 2 determinant. All it is the difference of the cross products when you start in the upper left-hand corner. You go A times D minus, that minus is from the formula that I'm giving you right now, B times C.
You don't need to memorize AD minus BC. Memorize the formula. The pattern.
You start in the upper left-hand corner, you go down that diagonal, multiply down that diagonal, minus, now you're at the second number on the first row, you start there, go in the opposite direction. Okay, this is number 10.
How it's written there. It's just absolute value bar, not the little brackets.
-1, -4, and 3, 1. So, here we go. We start at the upper left-hand corner, multiply down the diagonal. -1 times 1 is a -1. Minus, this minus is from the formula there. Then, -4 times 3 is -12. Watch out for those double negatives. This red minus came from the formula. -4 times 3 gave me a -12. -1 minus a -12, that's -1 plus 12, which gives me a positive 11.
See, the name of this method, if you were going to give it a name,
crisscross.
Yeah, we're doing crisscross.
Although technically it's the definition of a 2 by 2 determinant, but we'll say we're finding determinants by the crisscross method.
But once we get to 3 by 3, maybe the viewing example is not going to do crisscross. We're going to do crisscross.
Because that's what the physics teachers told me to do when this material was added years ago at the request of the physics faculty. I remember I was in a Calculus 2 class finding determinants, and the students in there, they said they'd found determinants in their physics classes, but they didn't find them the way I was doing it. I was expanding it down a row or column, whichever row or column had the most zeros in it, and they were using the crisscross method. I remember going to Dr. Zonka.
Talking to him. Oh, wow.
He passed away. You're right. But I remember talking to him. I said, do you really just use the crisscross method? And he said, well, yes. And I said, well, that crisscross method doesn't work for 4 by 4. And he said, we live in a 3-dimensional world. From a physics point of view, what is the 4th dimension? Why would they need to find a 4 by 4 determinant? And I was like, oh, well, okay.
Crisscross is easier.
Crisscross is easier, so that's what I'm doing. Now, did you type in that answer for number 10?
Yes, and we're ready to move on.
Okay, just show them. Okay, that's a 3 by 3. How do you find a 3 by 3 determinant? Tony hates it when I do this, but I'm going to write out the formula for you, okay?
I was the one that first wrote out the formula.
I know, but in the past you've told me, no one likes that formula. Stop writing it out. Okay, but I'm going to do it anyway. So, okay, here's the formula for a 3 by 3 determinant. It's like AD minus BC. For a 2 by 2, for a 2 by 2, there's only 2 diagonals. Okay, there's only 2 diagonals for a 2 by 2, but for a 3 by 3, you'll see that it's going to get a little messy. Let's see. The first row has 3 numbers, A, B, C. Then the second row, D, E, F.
At this point,
G,
E is not 2.71828. F is not function.
I is not imaginary unit. It's just representing arbitrary.
The first 9 letters of the alphabet represent 9 numbers.
Arbitrary numbers. Okay, here it goes. Here's the formula. It's left parentheses. A times E times I plus B times F times G plus C times D times G, close parentheses, C times D times H, thank you, that is an H, minus, open another parenthesis, C times E times G plus A times F times H plus B times D times I.
Is this a formula you got to memorize? No. It's a pattern you've got to remember. Do y'all see the pattern? I bet you see the first one, A-E-I.
There's more than just 2 diagonals. With a 2 by 2 determinant, there's only 2 diagonals, one falling from left to right minus one falling from right to left. So here we have that first one, A times E times I. My advice to you, that gave me the A times E times I. Here's the trick. Recopy the first 2 columns. That ADG, I shouldn't have put those equals there. ADG and BEH. BEH. You have 3 diagonals falling from left to right. You always start at that first spot. A times E times I, then move across. B times F times G, C times D times H, and now we're going to go in the opposite direction. We're still positioned at that C. Okay, so we have a minus. C times E times G, A times F times H, and B times D times I. You have 3 diagonals falling from left to right, minus 3 diagonals falling from right to left. You're probably right.
Well,
look at that mess, I think.
I used to always state that formula. Now,
but you have to memorize the formula.
Recopy the first 2 columns, and then start with multiplying the diagonals.
Okay, so we have 3. Let me write this down. 3 negative. And make sure you don't miscopy something, because if you do, then it's going to throw your... You know, when you're multiplying, what number should you hope you have a lot of for determinants like this? What's the easiest number to multiply anything by? 0? So when you're looking here, you should be hoping there's a lot of zeros. Here there isn't, but switch over. I'm going to recopy. Make sure to miscopy it. Yes, okay. Recopy the first 2 columns. 3, -5, -5, and 1, 3, 7. It's going to be parentheses minus parentheses. And here we go. 3 times 3 times 7. No, 3 times 3 times -7. 3 times 3 is 9, times -7 is a -63. Move over. Oh, 1s are nice. 1 times anything is anything, so that's nice. 1 times 1 times -5 gives us a negative 5. And 2 times negative 5 times 7. 2 times negative 5 is negative 10, times 7 is a negative 70.
See what it did? Multiply, multiply, multiply. Sometimes these numbers can get sort of big. You might need a calculator if the numbers are too big and the multiplication starts getting messy.
And now I think I will, okay, I'm going to use this color. I'm positioned at that 2 where we left off on that third diagonal. Now I go the opposite direction. 2 times 3 times negative 5. 6 times negative 5, that's a negative 30. 3 times 1 times 7, that's a positive 21. And last, 1 times negative 5 times negative 7 gives me a positive 35. Let's see. Now work inside the parentheses. I'll see people, they'll take that minus and distribute it through that second set of parentheses. I don't do that. I simplify inside the first parentheses, simplify inside the second parentheses, and then perform the subtraction. Negative 63 minus 8 is a negative,
minus 5.
Negative 63 minus 5 is a negative 68 minus 70, that's a negative 138. Minus, this minus here is the minus from the formula. Working inside the second set of parentheses. Negative 30 plus 21 is negative 9. Negative 9 plus 35, is that a positive 26? Negative 138 minus 26, is that giving me a negative 164? Is my mental arithmetic correct?
Mm-hmm. That's right. Any questions on this? See how he's gotten that?
Let's make a note next semester. This thing looks too messy there, so we'll just go to showing them how to find it.
Oh, I messed up.
I messed up. What did I mess up on?
Let me see. Where did we mess
3.
up? Oh, wait.
Negative
Let's
5.
check and make sure you
Negative
didn't
5.
miscopy it.
1.
Oh, you did.
3, 7.
Oh, my gosh.
What? I didn't miscopy.
Yes, he did. Do y'all see it?
Do y'all see it? Okay, this is just an example. This is just an example. Okay.
Now you'll do number 11.
Now I'll do number 11. This is not number 11. Notice I accidentally put a negative 5. I put 2 negative 5s.
Yeah.
Yeah.
And I want to see if there's any other place you miscopied and I didn't catch it.
The bad thing is I looked and double checked. But, you know, once you make a mistake like that, it is extremely hard to spot it, okay? That's where I rely on y'all, okay? Y'all let me down, I'm telling you. So we're just going to keep y'all longer now, okay? We have another problem to do, you see?
Now we got to do number 11 and 12.
The real number 11. So it's
recopy what you wrote up there, but just that second 5 is a positive 5. How did I not catch that?
1, 3, 7. Okay. Okay, so here we go. It's going to be big parentheses minus big parentheses. So
this time you're going to do it right.
This time I'm going to do it right, okay?
Ignore that.
Oh no! Why did I do that? 3, negative 5, 5, 1, 3, 7. After you do this a while, you can just see the, the diagonals without having to write out those numbers. But I'm writing them out. So, a negative 63.
See, like
plus
here's a
5.
positive 5.
I had a minus 5 because of the way I had the wrong sign. And this is a negative 5 right here. It's hard to tell, but what is that, a minus 70? Now we're going the opposite direction. It's going to be, this is going to be a positive 30. Let's see, something, okay, I'll use blind. That should be a positive 30. Okay. One little, and I think I probably said something like one little sign mistake will throw off everything. 1 times negative 5 times negative 7, that gives me a positive 35. Negative 63 plus 5 is a negative 58 minus
70, negative 128.
Negative 128, yes. And minus, that's what, a 51 plus a 35. 51 plus 35, is that an 86? Negative 128 minus 86, is that going to be a 214?
Negative.
Negative 214.
Try the punch thing. Let me erase this wrong answer. Negative 214. So that one little sign really had us off by a lot. One more of these, and we'll try not to make a mistake on this one.
Okay. Oh, I see some zeros. I like that. Multiplying by 0 is always easy. And 6 negative
6, negative 4, 2. Negative 3, 2, 8. And 2, negative 3, 2, 8. 2, 0, 0. Okay.
So we have parentheses, minus, parentheses, and why do I like those zeros? We always start in the upper left-hand corner.
If you start here, if you start doing the other diagonals, if you start there, you're going to get the wrong answer every time.
You'll be wrong by a sign. Okay, 6 times 2 times 0 is? That's why I like zeros. Negative 3 times 0 times 2 is another 0. Suppose a whole row or column was 0. What do you think the determinant would become if you had one whole row that was 0 or one whole column that's 0? The determinant would turn out to be 0. So if you have one where the entire row or column is 0, the determinant's going to be 0. 2 times negative 4 times 8 is a negative 64. And now we'll go in the opposite direction. We're still positioned at that 2. 2 times 2 times 2 is 8. And what are the other two determinants? 6 times 0 times 8 is? And negative 3 times negative 4 times 0 is 0. So we have negative 64 minus 8, which gives me a negative 72. And there are all sorts of generalizations we can develop and prove if we wanted to involving determinants.
Okay.
If you have one row or column that's all 0, the determinant's 0. Here's something else. If you have two identical rows or two identical columns, the determinant's 0 as well. But any questions? we are ready to pick up with Kramer's rule,
which will connect determinants and systems of equations. Well,
but we will do that on Monday. That's the Monday before Thanksgiving. And we'll be doing this. And that's going to be what, 11 dash, is it 26 or 25?
No. Oh, wait. Yeah, maybe. I don't remember the exact date.
I think it's 26.
Any questions before I stop recording?